Hello, good day everyone. Welcome to our lecture for today. So this time we are going to talk about another method of solving problems with the motion of particle. So we'll use the method known as work and energy. Alright, so before we begin, let us have these objectives first. At the end of the lesson, you should be able to solve problems involving work and energy using the principles of work and energy and the law of conservation of energy. So there are two methods introduced in this topic class, but our focus for this video is just the first method. Okay. So previously, problems dealing with the motion of particles were solved through the fundamental equation of motion. That is, summation of forces equal to the product of the mass and the acceleration. So current topics, as mentioned a while ago, introduces two additional methods of analysis. And as I said, we'll focus only the first method in this video class. So the other method will be discussed in another video. So the first method is the method of work and energy. The method of work and energy directly relates force, mass, velocity, and displacement. The other method, the method of impulse and momentum, directly relates force, mass, velocity, and time. Okay, so here's the illustration of this concept. We have here the a figure showing us the particle moving from one point to another point with the force applied. Okay, so assuming that initially the particle was in this position at point O, and then it moves, for example, and a force applied and it moves in this direction at this new position at point A with this position, no, from point O to point A. And it moves to the next position, point A prime, with a differential vector dr. Okay, so this is what they call dr here. It's called particle displacement. All right, so to find the work done, work of a force done in this particular scenario. So we have here the equation representing the work done of this force. So work of the force is given by the differential u. So differential work, a small amount of work done is just the vector force multiplied by its um, differential vector dr. Okay, so that's the first equation of our work, no? Work, differential work. All right, and differential work can also be uh, defined as the product of the force F, in this particular illustration, multiplied by the displacement ds. So again, assuming that the particle, this particle here is at this position initially, and it moves at this position at A1, covering a distance of S1, all right? And then from this point, it moves further to this position A. So with the displacement S, all right, and it moves farther, no? With the force applied, moves farther to this new position A2. Now with reference to this fixed point, so this is our S sub 2, okay? New position of our particle, assuming that this particle moves farther at this point. So we have S sub 2. And then from this position to that position, we have what we call uh, ds. This is the differential ds, the differential displacement. Okay, so we can also define the work done. No, work done uh, due to this force is equal to the F, the force F applied, multiplied by ds, this differential uh, displacement, multiplied by the cosine of this angle alpha. Okay, cosine. So we have the differential of work. So du is equal to f ds cosine alpha and it is also equivalent to the summation of the forces along the x-axis multiplied by the differential displacement along the x plus the force along the y-axis multiplied by the displacement along y-axis plus the force on the z-axis multiplied by the displacement along the z-axis. So this is for the three-dimensional scenario. Okay. So work is a scalar quantity. That is, it has a magnitude and sign, but not direction. All right. So remember, work is a scalar quantity. Right? This is scalar quantity. It has magnitude and sign, but not direction. All right. But not direction. So you should remember this concept always. Okay. So dimensions of work are length times force. Okay. So when you have work, so in this case we use U to represent work. So this is just the product of the length. So we can call the, and then force. We have length times the force. Or in some uh, cases class, we use the formula, no? In calculus, integral calculus, we have work equal to Fs. So F here is the force, and then S is the length, the displacement. Okay, so this is taken from this concept from our integral calculus. And even in physics, we discuss this. Okay, so remember that 1 joule equal to 1 Newton meter, or 1 meter times 1 Newton times 1 meter. And that is also 1 pound, 1 feet pound, which is equivalent to 1.36356 joules. Okay, so remember these equivalent units. So work of a force during a finite displacement. Okay, so finite displacement, so these are clear uh, points where the particles move. Okay, so initially it moves from this position point O or point 0. It moves at this point at A1, and then it moves to point A, and then moves to point A2. So there's a finite displacement of the particle. Okay, so in this particular case, so we have here work done, no, work done, or work done from this point, no, from initial point A1. Okay, so at this point, and then up to the second point at A2 at this point. Okay, so we can solve for the work of force as this is represented as U 1 to 2, meaning from this point A1 to point A2, equal to the integral of the force, the vectorial force, multiplied by dr. Okay, and our dr here is this one. You see this part here? This is our dr. You have the arrow. So this is our dr. Okay, so that is the vector. This is vector. This is also vector. So this is the dot product of the force, vectorial force, and the vector displacement. Okay, so the limit here is E1, the lower limit E1, and the upper limit is A2. So we have, this is also equivalent using the other formula class shown a while ago in terms of the angle alpha. Okay, so in terms of the angle alpha, we can have also this work done from A1 to A2, 1 to 2, equal to the integral of the product of cosine of cosine, sorry, f times cosine alpha multiplied by ds. So our limit this time is s1. Okay, so s1, that is the displacement from point 0 to a1, and s2 from point 0 to a2. So this is our These are our lower limits, and sorry, lower limit, and this is our upper limit. Okay, so we have therefore this one is equal to the integral of f sub t times ds. Okay, so another illustration, uh, something like this. So this is also equivalent to the integral of f, this f here, f of t, all right, f of t multiplied by ds. So we can have s1 is the distance, no, coming from this point up to this. So this is our s1. Okay, this is our s1. And we have s2. S2 is again from the fixed point O up to this one. So this is our s2. Okay, so we're just when we speak of work, this is just the area, area under this curve. Okay, area under this curve from S1 to S2. So work is represented by the area under the curve FT, this FT curve FT, plotted against S. So this is the horizontal axis, which is S, the displacement, and we have the vertical, which is the force as a function of time, T. Okay, and this is also equivalent to the summation, no? The integral of the summation of all forces along the x, y, and z with the limit e1 to a2. Okay, so again, just to highlight this one, so you can use, you can determine the work of a force using this formula, and this means that this is just the area under this curve, having the limit, no, from s1 to s2. So these are limits of the integral. Okay, now work of a constant force in rectilinear motion. So we can also determine the work of a constant force in a rectilinear motion. So we have here, for example, again, this is our reference point, that is a fixed point where the particle moves initially at t equal to 0, assuming that the particle is here at point O, and at t equal to t1, for example, it moves at this particular position at a1. All right, and then moves at this point A. Uh, we have, and then force applied at this point, and it moves, particle moves at this point A2. So with a direction of the force at this angle. All right, so we have here the displacement delta x. We can call it delta x, the difference from this, because this is E1 class. Sorry, this is A2 from this reference point. So this is our A2. Okay, from that is A2, and then from here to there, meaning from O to this point, this is our E1. All right, then we can have the difference. So if you want to solve for this one, for this particular part, okay, so this is just A2 is A2 minus A1. So A2 minus A1, so this is our delta x. Okay, so this is our delta x, the difference. Okay, the difference of the displacement, or okay, so the difference between A2 and A1. Okay, so this is our delta x. So our work done from E1 to E2, 1 to 2 is equal to the product of F, this is the force applied, times the cosine of this angle alpha multiplied by this displacement from E1 to E2, that is delta x. So that is equivalent to A2 minus E1, and then you will be able to solve this delta x. Okay, so I hope it's clear and well understood. Okay, so let's proceed. So work of a force of gravity. no, in this particular example class. So it can be that the particle is coming from here, then going to the right, or it can be from here, from this position, and then moves down. Okay. All right. So work of a force of a gravity in the scenario class is equal to du. That is the differential work. Now we're talking of a very small work done, but this due to the weight of this particle. Okay, so this is defined as differential u, differential work, equal to force multiplied by displacement dx. Force sub x multiplied by dx plus force sub y multiplied by dy plus force along z with respect to times dz. Or in this particular example illustration, we have du, differential work, is just the product of the weight of the particle, and this is negative class. Weight of the particle negative, which is w, weight. I'll explain to you why this is negative now later on. Multiplied by dy, this is differential way. It means that assuming that the particle is at this point and then it moves down up to this point, it moves because of the weight. So we have to multiply just the weight of the particle multiplied by this displacement, the vertical displacement. Okay, so vertical displacement from initial position to this next position. Okay, so that is minus w dy. Okay, now to calculate the work done, or the work from A1, no, from A1 to A2, from 1 to 2. So assuming that the particle is coming from here and it moves at A1, it moves at A and then moves further at A2. So we have work from A1 to A2, that is U sub 1 to 2 equal to the negative. No, this is negative integral of the work. Okay, because we have differential U here. So this is the differential U. So to get the U, you have to integrate both sides. Okay. So integrating both sides, so we have du. Okay, so we integrate this one. We integrate this. So integral of du is u. Okay, from a1 to a2, 1 to 2, equal to the integral of w. So this is the right side. They need a negative. We put the negative outside, multiplied by dy. Okay, so the limit here is from y1, because this is the initial position of the particle, and the next position here. So this is the upper limit, this is the lower limit. Okay, or equal to, so the weight is a constant, so you can isolate this one and integrate dy. So the integral of dy is y. This so from here, so it's something like this class. So from this part, since the weight is a constant, so we have minus w, then integral of dy. So integral of dy, then the limit is from y1 to y2. Okay, so equal to, substituting the limit using your skills in integrals, we have minus w. So integral of dy is y, right? And the limit is from y1 to y2. Okay, so when you substitute the limit, so that's why you have uh, minus w. Okay, minus w, this is negative, then multiplied by upper limit, which is y2, y sub 2, minus y sub 1. Okay, so that's why you have this resulting equation here. Okay, so this is our, and you see that the delta y, y sub 2 minus y sub 1, this is just equal to delta y. So So this particular difference, no, this difference is just equal to delta y. So that's why our equation reduces into minus w multiplied by delta y. Okay, and then we know in our differential calculus, so we can have the delta y could be approximated as dy. So that's why we have our work done from work of a force from A1 to A2 is equal to uh, minus W times delta Y. Okay, because we're considering this, and then our delta Y, take note that our delta Y is approximately equal to dy. All right, so this is delta Y. So I hope it's clear with your class. So the symbol is approximately. Okay, so work weight is equal to the product of weight W and vertical displacement delta Y. Okay, so this is the definition of work of the weight. And as I mentioned a while ago about the negative, so we have here work of the weight is positive when delta Y is less than zero. Okay, less than when, what does it mean less than zero? Less than zero means negative. When our delta Y is negative, so it means that the weight moves down, from here going down. So in that case, because you have small minus big, so you'll get a negative result. So negative multiplied by negative, so you have the positive. So that's why work of weight is positive. So positive when delta y is less than zero, meaning if delta y is negative. So when the weight moves, and that happens only when the weight moves down. Okay, so I hope it's clear with you. Now another problem here is something about spring. We have a spring in this position, spring undeformed. So it means this is the original distance from this reference point B up to this point. So we have A sub 0, meaning there's no force applied yet. So magnitude of the force exerted by spring is proportional to deflection. So it means that force is equal to directly proportional to its displacement. So force equal to K times x, where K is the spring constant that is in Newton per meter or pound per inch. All right, so K is spring constant, Newton per meter or pound per inch. All right, so assuming that the spring is stretched and it moves, this point moves at this point at A1 and with a displacement of x1. Okay, so there will be a force. Of course, the force applied to stretch the spring, so there will be a counter force, that will bring it back to its original position. We call it F. So assuming that the force applied F at this point, when this part reaches at this point A, so we have a force F that will counter that force applied to stretch it. And if further stretching makes this part of the spring reaches at this point at A2 with a displacement of x2, then mathematically we have work of force exerted by spring is given by this definition, that the differential work, equal to negative F dx. Negative F dx, where our F, as defined here, our F is equal to the product of the spring constant and the displacement x. So therefore we have, instead of f, we substitute here. So we have negative kx dx. Or to find the work done from this point, from this point to this point. meaning stretching at this point up to this point, then we can solve the the work, the work of a force by integrating. No? We have to integrate this equation class. Okay, so we have du equal to the negative of kx dx. So integrating both sides. So integrate this. So we have u from 1 to 2 is equal to x. Sorry, we still have x here. We missed the x. So we have kx dx. And we know that k is constant. You put the constant outside the integral sign. So negative k integral of x dx. And our limit is from x1 to x2. So x1 to x2. This is our limit. Okay, so substituting the limit or applying the integral of x to the n equal to x to the n plus 1 divided by n plus 1. So we have therefore x squared, okay, x squared divided by 2. Then the limit is from x2 to from x1 to x2. So this is x2. Okay, then substituting, so we have here the result, no? So after you substitute, we have therefore 1/2. So from here, so 1/2, then so you still have k here, and take note this is negative. This is negative, so negative 1/2. So substituting the limit, so you have x sub 2, or this is x squared, no, x1, no, x2, then this is squared minus x1 squared, or rearranging. So this is negative, so when you rearrange it, so you have take the positive, so 1/2. So negative times negative, so that becomes positive, so write x1 first. So x1 squared, then multiplied by 1/2, and then negative times positive, so that becomes negative. So this time this is negative x2 squared. Okay, so that's why you have here the result is, or you have to multiply. There's still k here. There's still k. Also, there's still k. Okay, let me rewrite it. So we have 1/2 k multiplied by x2 squared. Sorry, this would be x1 squared and minus x2 squared. Okay, so it's just like this one. I just factor out one half here because we have one half on the first term, one half on the second term. So I just factor out one half and also the k. So that's why we have here one half k x1 squared minus x2 squared. All right, so this is another expression for the work of force exerted by spring. Okay, so work of force exerted by spring is positive when x2 or x sub 2 less than x sub 1. Meaning, if the result here, uh, if the value of x sub 2 to something like this, x sub 2, in this case, x sub 2 is greater, no? In this case, class, our x sub 2 is greater than x sub 1. So we can expect that the result here, so the result here it would be negative. Okay? So, but if it happens that uh, if it happens or x sub 2 is less than x sub 1, then we can expect that the work of force exerted by spring would be positive. Why? Because when you subtract the difference of this x1 x1 here would be negative, then you have a negative outside, so that becomes positive. Okay, so that's the concept plus work energy. So work of force exerted by spring is equal to negative of area. Okay, so I delete this one first to give us a clear view of this part. So this is the graphical interpretation class for the spring. Okay, so it says that work of the force exerted by a spring is equal to the negative area of the negative of area under curve f plotted against x. So this is our x-axis, this is our f-axis, and we have here x1, x2, and this is our delta x. Okay, so as you exert the force f1, so for example the force exerted at this point is f1. Okay, and then there's a displacement of x1 from the origin. Okay, and then in the force exerted uh, is increased, for example, to f2. Then this is the displacement now, x2. All right. So this is the graph of the equation of the force F equal to kx. So k here is the spring constant. Okay, so this is positive, right? F equal to uh, positive kx. So when you graph this, you will see this graph. But using the previous concept, now we have here that F is equal to the negative of F is equal to negative, or F is negative because this is spring. So the spring will go in this direction. The force is going in the direction. So opposite to this force applied to stretches the spring. So we have negative F. That's why we have a negative here. But originally F is equal to this one. So we have this. When you graph this equation F equal to kx, so you will see this one. All right. So the work of force exerted by spring is equal to the negative area. Negative of area under the curve F plotted against X. So the work of force exerted by spring is given by U work. Your U here stands for or represent the work from one, no, from this position to that position, from 1 to 2, from F1 to 2, from F1 to F2, with this displacement from X1 to X2 is equal to minus 1/2 of F1 plus F2 multiplied by delta x. Okay, so remember this. No? This is very important formula class for a problem that involves spring. So work from F1 from 1 to 2 is equal to negative 1/2 of the sum of the two forces F1 and F2 multiplied by delta x, the difference of this displacement. Okay, so I hope you're ready now for our problem. So to summarize here, so force which do not do work, so it means that there's no displacement. So d is equal to 0, or cosine of alpha is equal to 0. Okay, so force which do not do work, so it gives us d is equal to 0, or cosine of alpha is equal to 0. And reaction at frictionless spin supporting rotating body. These are the scenario class. So the reaction at frictionless spin supporting rotating body, or reaction of frictionless surface when body is in contact moves along the surface. Right? Then reaction at a roller moving along its track, and weight of the body when its center of gravity moves horizontally. Okay? Now consider a particle of mass m acted upon by the force, vectorial force F. So from our definition, from the concept that we have discussed earlier, that force, Ft is equal to, force is just the product of the mass and the acceleration. Okay, and we know that acceleration, we have defined it before, that our acceleration is just the derivative of the velocity. So derivative of velocity, when you have v, then you take derivative of v with respect to time. So that is our acceleration. Okay, so in this case we have a, now we have t as a function of time, we have acceleration as a function of time. So a sub t is equal to dv over dt. So substituting this, that's why we have mass times the dv over dt is just the acceleration. So this is the acceleration at. Okay, now uh, we can, if we are going to multiply this by from this equation, if we are going to multiply this part, we have, say, originally we have m times dv over dt. So let us now manipulate this expression. So take note, this is our f, this is our f sub t. Okay, so now if we are going to manipulate this, like for example, if we are going to multiply this on the right side, if we are going to multiply this by ds, multiplied by ds over ds. So are we changing the expression, or are we changing the equation if we multiplied this by ds over ds? So we're not changing, because ds over ds is just equal to 1. So it seems that nothing happens. But if we really do multiply this by ds over ds and then rearrange, like in this case, we have m. Now, instead of, so m is equal to dv. So we replace the position, we have dv, this dv here, and divide this by ds. Okay, so divide this by ds. And we have times, at the numerator we have ds, then divide by dt. So are we changing the equation? Sorry, this is ds. Are we changing the equation, class? So we are not, no? We are just rearranging. So instead of dv divided by dt, we divide it by ds. Okay, so dv over ds. And then ds, instead of divide by ds, we divide it by dt. So we're just rearranging the position of ds and dt. Okay, so we have the reason why we're doing that, class, so that we can manipulate the given expression. Okay, so we know that ds over dt, if you can still remember this in our previous discussion, this is just if you have the displacement, no, as or position as a function of time f sub t. So when you take the derivative of s with respect to time, okay, so we have derivative of s with respect to time. So remember this in our discussion earlier this term. So this is just the same as f prime of t, and this is our velocity, right? You still remember that derivative of s with respect to t is just the velocity. Okay, so that is just v. So that's why we can write this, or we can rewrite this as m multiplied by v. Okay, so because this is equal to v, then multiplied by dv over ds. Okay, so dv over ds. So that's what is shown here. All right, then after that, if we are going to multiply both sides by ds, or just simply cross multiply ds. So when you cross multiply ds there, so we have f of t, or f sub t multiplied by ds, so equal to m times v times dv. Okay, so this is what is shown here, this one. So that's the derivation, class. All right, so from that particular resulting equation, if we are going to integrate, no, if we are going to integrate both sides, it means that if we're going to integrate both sides, so I have, sorry, we missed to write ds here. We still have ds here. Uh, sorry, I missed to write the ds. So because we cross multiply ds. Okay, so cross multiplying ds, so we have ft times ds and equal to this. Okay, so ft times ds equal to mv dv. So integrating both sides. All right, so integrating both sides equal to this one, m. So m is a constant. Okay, so I'll show you the solution here. So integrating both sides, integral of ft ds equal to m. The mass is constant, so you can put this outside. The integral of v dv. Okay, integral of v dv. So the limit here, as you can see here, the limit is from s1 to s2. From s1 to s2, and then here the limit is from v1 to v2. So why is 1 to s2? Because we have s, we're talking of s, so naturally from s1 to s2. Okay, so this is our limit. Lower limit is 1. Here the limit is, upper limit is 2. And then here we are talking of v, so this would be v1, velocity v1 and v2. Okay, so these are the limits. So manipulating, so we have here 1/2. Okay, so I'll just erase this one, class, anyway. You have seen already how it is done. Just to make clear of this part here. Okay, so after doing that step-by-step solution, okay, so we have here integrating, so we get this. Um, the result of this, when you integrate, this would be, okay, so 1/2, no, because v, apply the integral formula. So we have the integral of, if you have integral of u to the n, u to the n dx. So this is equivalent to u to the n, u to the n plus 1 divided by n plus 1. Okay, of course, you have the constant of integration plus c. All right. Or if you have the limit, then you just substitute the limit, so you don't have the constant of integration, so you don't need to write this because you have the limit. Okay, so substituting the limit. Okay, so we have 1/2, right? This is 1/2. Why 1/2? Because this would be uh, v squared, no? This becomes v to the n, so understood to be 1 power 1, so this becomes 1 plus 1 is 2, so v squared, that would be v squared divided by 2. Okay, so you can remove the fraction and write it as 1/2. So something like this, class. If you have integral of v dv, limit from v1 to v2. Okay, so this is equal to v squared. Okay, v squared using this formula, using this, over n plus 1. N here is 1, 1 plus 1 is 2, then we have 1 plus 1 is 2, so v squared. Then the limit is from v1 to v2. Then substituting the limit, so you have, you can write this as 1/2 times v. V, the upper limit is, in this case we have mv, we have m here, the constant. Okay, so we have times m we have times m here, and substituting the limits, that is v2 squared minus v1 squared. Okay, we just factor out 1/2 of m, 1/2 and m. So this is minus v1. This is v1 class, v1 squared. Okay, so we have this resulting. We just factor out 1/2 m, 1/2 of m, and then we rewrite it this way. Okay, so that is integrating from a1 to a2, from a1 to a2. So where is this s1? So s1 class is assuming this is our point O. Okay, point O, and then here, from here to there. So this is our s1. Okay, so this is our s1 here. Then from here to there, so traverse from here to there. So this is our s2. Okay, and from, all right. So we have here in this illustration, this is our Ft. This is the uh, tangent, no? The tangent line, tangent to this curve. Our Ft here. So remember our Ft here from this illustration. This is the tangent to the curve. This is our curve, the path of the movement of the particle. Our Ft is this one. So T here is means tangent. No? Ft means force tangent to this path of the particle movement. And we have Fn here. Fn, it means this is the force that is normal to this path, or normal to the tangent line. That is why we have Fn. And this is the resultant force F. So take note, the F here is our resultant, no? Resultant force. The force between the Ft, the tangent, force tangent to the curve, and this is a force normal to the curve. So that is F, that is the resultant force. Okay, so I hope it's very clear. And now we have here a definition that the work done, the work of a force from from 1 to 2, meaning from this point here, from E1, or from E1 to 2, or E2. So that represent that statement equal to T2 minus T1, where T is the kinetic energy class. So T2 minus T1. So that is our definition. T2 minus T1. All right. So remember that work is just the difference of the, the kinetic energy from the difference of kinetic energy from this position 2 of E2 and 1. So the difference. And T is equal to, so remember this, T is equal to 1 half mv squared. Okay. So T is 1 half mv squared. 1 half mv squared. So in other words, this is the kinetic energy class. So 1 half from our derivation here. So 1 half m v squared. So here v is the difference. Difference. Okay. So this is our kinetic energy. Remember this. This is a very important concept, class. Okay. And the work of force is the vectorial force. The work of force is equal to the change in kinetic energy of the particle. So the work of force, remember this very important statement. The work of force, which is the vectorial force, is equal to the change. No? The change equal to the change of the kinetic energy of the particle. Change of the kinetic energy of the particle. Okay. So remember that kinetic energy is 1 half mv squared. Remember this, kinetic energy T is 1 half 1 half mv squared. So the work from 1 to 2 is equal to the difference of the kinetic energy, T2 minus T1, where T is 1 half mv squared. That is the kinetic energy. Okay. Units of work and kinetic energy are the same. So remember, units of work and kinetic energy are the same. So we have kinetic energy equal to 1 half mv squared. So that is kilogram. The mass here is in kilogram. And unit V is meter per second, but that is squared. So meter per second squared. Okay. And kg is equal to, you can separate, no? You can separate the m here. You can break the m into two parts, m times m, so that is m squared, and you rewrite it this way. And we know that kilogram meter per second squared, that is in terms of Newton. All right, meaning the equivalent of kilogram meter per second squared is Newton. Then you multiply that with m meter, so Newton meter, that is equivalent to joule. Newton meter is equivalent to joule. Okay, so therefore the unit of work and kinetic energy are the same. So hope this is clear with your class. And the next concept is something like this. For example, we wish to determine the velocity of pendulum bob. Name the pendulum is bob at A2, meaning at this point here at A2. Consider work and kinetic energy. Okay, so the force P, so force P, you consider this one here. So there's a force that holds, no? When the position is at A, so there will be a force going in the direction to hold this pendulum. So that is our force P. So force P acts normal to the path, and does no work. Meaning normal, this is the path of the pendulum. So this is normal, meaning perpendicular. So the P here is perpendicular. Okay. So at this point, at A, so we have a force here, counter, no? Counter force, because this is a weight. So it counter. So the work here, the P here acts normal to the path and does no work. P does no work. P does no work. So in this case, we have T1, no? T1 meaning the tension here, the energy here at this particular at E1. So T1 plus, okay, so the kinetic energy T1 plus U1, meaning the work from 1 to 2, meaning from this position to this position. So that is work, no? Work is equal to T2, meaning uh, the work here, the kinetic energy here. Okay, so since there's no work done, no? So T1 plus U, or the work done, work from this point E1 to 2, E2, is equal to T2. All right, but this one, so there is no displacement for, so this is equal to 0. And this work done, so from the definition, work is equal to Fs, no? F times S, or we have work is equal to length, no? Length times the force. So it means the work, no? When you consider this one here, so the work is just the weight, no? The weight of this pendulum, multiplied by this length. Okay, so that's why we have here for this part the work from 1 to 2, from here to this position, is just the product, no? The product of the weight, no? Product of the weight multiplied by the length of this. Okay, so the length of this, which is L, which is constant with this one. This is L, this is also L, this is also L. So just the product, no, the weight. By the way, class, don't be confused. I'll change this. You might be confused. So I'll use U instead of W, because we use W. That's why we didn't use W in our work class, because it might confuse, no? Because we use W for weight. So instead we use U to represent for work. Okay, so we use U so that you'll not be confused with W here. W here stands for the weight. All right, so this is T1 that is equal to 0. So the work from A1, from 1 to 2, so that is just the product of the weight multiplied by this arm. This is the length of this arm. And that is T2. And T2, and we know that T2 is, we have from our definition a while ago, we have T2, or T is equal to 1 half. That is 1 half, if you can relate it to our previous slide, 1 half mv squared. All right, so that's our definition. All right, so for T2, and we know that the mass is just ratio of the weight, no? Ratio of the weight and the gravitational acceleration. So that's why we have here, instead of m, so we write here w divided by g. So that represent our mass. Okay, so our question becomes this one. Okay, instead of mass, we use w over g, v squared. So now we have w on the left side, we have w on the right side. Okay, so we have w on the left, we have w on the right. So w divided by w, so this will be gun, right? So that will be gun. So therefore we have, and what is left here, it becomes L. So we have L equal to V squared, no, V squared, V sub 2 squared. Then you have over G, okay, over G, and then you have 1/2. All right. Okay, I will rewrite this. I will rewrite this. So this will be, what is left here is just the L, right? Then cross multiply. So when you cross multiply this, so you have 2 times G times L and equal to V squared or V2 squared. Okay, so the 2 here is subscript because we have 2 here, so we use subscript. The velocity is 2. So now to solve for V sub 2, so you take square root on both sides, so that's why you have 2 square root of 2GL equal to V squared, or sorry, V2. Okay, so this is it. So that's why we have here the velocity, no? The velocity at this point here. Okay, so from this discussion class, velocity found, no? The velocity were found or was found. Okay, I'll erase this one. So velocity was found without determining expression for acceleration and integrating. So we have another way of finding the velocity using this concept class. Okay. Now all quantities are scalars and can be added directly. And forces which do no work are eliminated from the problem. All right. So principle of work and energy cannot be applied to directly determine the acceleration of the pendulum bob. So here, from this illustration, so taking into consideration the same problem, so we can rewrite this into this, represent this diagram into this, and this is equivalent to this one. So from here, we transform this diagram into this diagram, and from here to this one. So mathematically, again, this is the derivation. We get V sub 2 equal to the square root of 2GL. So calculating the tension in the cord requires supplementing the method of work and energy with an application of Newton's second law. Right, so as the bulb passes through A2, so this one here, so because this is a pendulum, so it moves. When it passes through this one, so we have summation of forces, force normal, normal force equal to mass times the acceleration that is normal to this path of the movement of the pendulum. So we have here from this illustration, we can transform here. This is the force, no? That is the tension, the force P that holds the weight. All right. So equal to P, assuming that going up is positive. So we have P. Then weight going down negative. So P minus W equal to mass times the acceleration, and we change the mass in terms of weight. So we change the mass in terms of weight divided by the gravitational acceleration. So, and we have v v2 squared over L. So v2 squared over L, and then we transpose this to the other side. So this becomes P and equals W. So the negative W here becomes positive. Then we have W over G, this one. Then we know that we use this equivalent from our derivation. Our V squared is equal to the square root of, sorry, V sub 2 is equal to the square root of 2GL. Now, if you are going to square this, so when you square this, so V V2 squared equal to square both sides, so the right side becomes 2GL. Okay, so this becomes 2GL. Okay, so substitute it here. We have AN. By the way, our AN is the normal acceleration normal to the path of the movement of the pendulum. This is equal to V2 squared over L. Okay, so that's why we substitute AN here with this. And then we know that this V2 squared is equal to 2GL. Okay, from this definition here. So we have here J, we have G at the denominator, we have G at the numerator, we have L at the denominator, we have L at the numerator. So that cancels out. So we have W plus W times 2 is 2W. So summing up, so we have P is equal to 3W. So it means that the weight or the force, the force needed to hold this pendulum glass is 3 times its weight. So P is equal to 3W. All right. So that is our result of our calculations. We have work and power. So power, rate at which work is done. So the definition of power is just the differential work with respect to time. So we know that du is just the product of the vectorial force and the vectorial displacement dr with respect to time. In other words, and we know that this dr over dt is just dr is displacement. So derivative of displacement with respect to time, we know that is the velocity. Okay, so we can reduce the equation into vectorial force multiplied by the vectorial velocity. So that's our definition of power, right? And the dimensions of power are work over time, or force times the velocity. The unit of power are in watts or watt, and this is equivalent to 1 joule per second. And we know that 1 joule is 1 Newton meter, so therefore watt is 1 Newton meter per second. Or we can have the unit of power in terms of horsepower, that is equivalent to 550 feet-pound per second. And this is equivalent to 746 watts. So 1 horsepower is equal to 746 watts. All right. Now we have, when we talk about power, work and power, so we have what we call efficiency. So this is the symbol used of the word efficiency. So when we speak of efficiency, that is the output work divided by input work. Or we have the power output divided by power input. So that's efficiency. Okay, so that's the answer for work and energy. So I will end up my video at this point, and we'll have another video for our example. All right, so thank you very much and hope to see you again in our next video. Bye.